So continuing on from last lesson, we're going to talk about reference figures, reference curves, and then how to scale data to fit those reference curves. Now, if you'll recall, this plot over here on the right-hand side, this is what I introduced in the last lesson, where I said if you had a 1 kiloton weapon and you were a certain distance away from it, you could draw a vertical line from wherever that distance was till it met the curve. And then you could, of course, do a horizontal line to find out what's your peak overpressure. Now, this assumes that you're at some kind of an altitude, sufficient altitude, so that you don't have any shock ground interaction. If you do have that, then you kind of need to go to these other two curves where the Mach stem is present, and we can see where that bulging pressure zone from the interactions of the reflected and initial shock waves occur. So what we want to do is we want to be able to take any arbitrary yield weapon and scale it in such a way that we can use these plots to figure out what pressures that we're interested in. So we do this. It's the same formula, and we do it with 3 different variables. 2 of them are here. The other one is time, and we'll see that here in a second. But if we want to scale either our height of burst or our ground range distance, or to be honest, even a slant range distance, you take the figure that you have. So for height of burst, say that you have 10,000, the burst was at 10,000 feet. But the yield of your weapon is 100 kilotons. So what you would end up doing, let me get my little thing here. So you would take this equation, and to find out what the scaled height of burst is, you would simply say, all right, well, now remember this is all in feet. So say we had 10,000 feet, but then we're going to have a weapon yield of 100 kilotons. So then we're just going to divide that by 100 raised to 1/3. And that is going to be our scaled height of burst. Okay? It's actually really straightforward. And you can repeat this for your ground range or even slant range. So it's just one equation, and once you get the answer, then you go to your plots here and you find your scale distance, which now applies, and you read off where it ends up on the graph and then look at what the horizontal axis is. So in the case of these 2 left-hand plots, you need both scaled height of burst and scaled ground distance in order to correctly read the chart. So hopefully this makes sense, and this is very similar to what we've seen before. The only difference is that we're taking into account the differing effects as the yields of our weapons change. All right, so let's take a look at an example. So the first thing we need to do is we need to have some basic information, right? We need to know what the yield of our weapon is, and we also need to know how far away is it, both height of burst and the ground range. So we're going to start off, we have 25 kilotons, that's height of burst of 5,000 feet, and a ground range of 2,000 feet. So the first thing we're going to do is use this information to calculate our scaled height of burst and our scaled ground range. And so we do it pretty straightforward. So we say our new height of burst, which is scaled, that's going to be equal to our 5,000 divided by 25 raised to the 1/3 power. And our scaled range, that's going to be equal to 2,000 divided by the same thing, which is 25 raised to the 1/3 power. Now, when we do this, we find out that our scaled height of burst is going to be 710 feet, or 1,710 feet. Okay, and our scaled ground range is going to be 684 feet. So now that we have those two, we can figure out what is going to be the peak overpressure for this weapon at that height of burst and that ground range. So how do we do it? The way that we have been doing it, which is simply we're going to draw on a graph. In this case, I'm being able to use something like PowerPoint and having nice straight lines or like a Word document or something, very handy. So the first thing we're going to look at is where's my scaled height of burst? Okay, now there are 4 axes on this particular plot. So we have height of burst, which is going to be our y-axis, and then we have ground range, which is going to be the x-axis. However, the 2 different axes for height of burst, one is in feet, one is in meters, and same goes for ground range. So make sure you know which one that you need to be using. If you're in feet, use the one that says, that's the scaled height of burst in feet, and then similarly use the one that's appropriate if you're using meters. Now, for whatever reason, the scaled height of burst tags for both of those axes do not, in fact, have what units they're in. I just know which one is which. Generally speaking, the one with the bigger numbers is in feet, and the one with the smaller numbers is in meters. So if we draw our little line right around 1,700 feet, we draw it straight across. Then the next one we draw is the ground range line. And again, 684, almost 700 feet. So we estimate where that is, and then we draw a line. And then we look to see where the intersection is. It's almost right on that 6 psi curve. It's just a little bit off. Okay, but the next one down is 4, and the distance between these is huge. So you could say that right about here, that halfway, this would be 5. So this would be something like 5.8 or 5.9 psi, just as a kind of eyeball estimate. So that's it, and that's really all there is to it. Being able to scale, depending on weapon size, and using these charts to figure out, well, this particular chart to figure out what your peak overpressure is going to be. Now, I said that there was one more scaling law that we hadn't seen yet, and it has to do with time. And it has to do with the time of arrival of the shockwave at some distance away from your weapon detonation. And this is exactly the same thing as before, right? So we need to know how big was our weapon and how far away were we. So we do very similar. In this case, I'm going to keep it as a 25 kiloton weapon, but this time I'm going to put the height of burst at 10,000 feet and the distance away at the ground range also at 10,000 feet. So if we go ahead and run the calculations on those, which I have right here on the slide, we end up with both of them being scaled to 3,420 feet. Now this plot is to find out what that time of arrival is. So we have, very similar to what we saw with the height of burst and the ground range, we have this one simple equation that says basically take the time of arrival, the normal time of arrival that you would have, and scale it based upon the yield of the weapon. So we can do that. And the first thing we're going to do is we're going to say, okay, let's draw the line for my height of burst. Okay, and let's draw the line for my ground distance. Again, we have an intersection off of this curve right here, which if we trace it down is about 3.5 seconds. It's a little bit longer than that. So if this is 3.5, it's less than half. I'm going to say that this is probably about 3.2 to 3.3 seconds. Now, that is a scaled time. We scaled up the height of burst and the ground range. So what we're reading off of this chart is a scaled time for the shockwave to arrive somewhere. What we need to do is use this equation and find out what the actual time is going to be. Okay? So if we do that, we find out using approximately 3.3 seconds as our estimated scale time, we can take that equation and basically just multiply both sides by your yield term, and then we can solve for the actual time of arrival, which is approximately 9.6 seconds. And this should make sense to you. Remember when back when we were talking about the double hump curve, and how as weapon size increased, we started seeing that that it stretched out in time. So instead of it being over in a matter of seconds, like megaton yield weapons ended up being out to 20 seconds or even further. So it would make sense that the time of arrival would be, for 1 kiloton, if you found that it was 3.3 seconds, that if you jack that yield up to 25 kilotons, then it should be a bit longer for the same amount of distance. And this is what we're finding out here. So again, very simple. Take the information you have, read information off of a plot, and then if you need to, then you have to do maybe one more calculation like we do in this case. So now that we've used our reference curves and our scaling equations to determine peak overpressure and shockwave arrival times, let's take a step back and look at some other characteristics of the pressure part of a nuclear detonation that may be of interest. So if you recall in a previous lecture, I mentioned that there were two different types of pressure. There was overpressure, which is basically it's a measure of the shock front. And then there was something called dynamic pressure, which was a measure of the velocity or the pressure of the air that was being dragged behind the shock wave as it propagated out through the atmosphere. Now the shock wave has a velocity of its own. We can calculate, or we did calculate if you will, the arrival time in seconds of a shock wave given certain parameters, but we can also calculate what the velocity of the shock wave is. And the only thing that we need to do this is we need to know a couple of pieces of information. We need to know what's the yield of the weapon. Okay, we need to know what's the local speed of sound at whatever altitude we're looking at. And finally, what's the ambient pressure at that altitude? And so if we look at this top equation right here, titled shock velocity, surprisingly enough, this term right here is the local speed of sound. This is peak overpressure, which we can read directly off of the plot, which we just did. And then finally, what's the ambient pressure? That's right there. Okay? Now, where would you get these things? Well, as it turns out, E&W has a handy-dandy little table that has values such as this. So if we look over here, we have one column that is speed of sound in feet per second, and one is ambient pressure in PSI, and they're all in relation to some altitude. And they're all in, one's in feet, one's in PSI, and one's in feet per second. So if we know the altitude that we're at, and we also can look up what the peak overpressure is on our reference graph using our scaling information from the weapon yield information and the height of burst and ground range. So we have to go through all that first, right, to find the peak overpressure. Then we can simply come over to this chart and pull the last two pieces of data that we need, which are the ambient pressure and the local speed of sound. Once we have those all together, we simply plug them into the equation, and voila, we have the calculated shockwave velocity. Now the wind velocity, the air behind the shock front, we use the exact same three numbers to calculate that as well. So if we look at our equations over here, we can see that we have P and P naught, and then we have C naught, or our local speed of sound. And then finally, peak dynamic pressure is of interest because that's one of the things that we use to measure the damage that the pressure component of a nuclear weapon detonation is going to inflict on something in the environment, like a building or a car or a house, something like that. So if we wanted to find out peak dynamic pressure, surprise, surprise, we still only need those same three variables. Okay, so to calculate all of these things, we first have to find out what the peak overpressure is. Okay, and that's using our reference curves and those scaling equations. Once we have that, though, it is a literally simple table lookup for the other two values. And then the hardest thing about this is inputting the formula into Excel or MATLAB or something, or inputting the numbers into a calculator so that you could just, end up with the number that you're looking for. So it's really not that complicated to get these three values by themselves. Again, still have to do the reference curve thing. Now, you'll probably notice that there are a couple other columns here. One is the ambient temperature at certain altitudes. But then there's three of them that are over here, which are called scaling factors. Now, these scaling factors take into account that at altitude, we have different characteristics of the air than we do at ground level. And our reference curves are all built around standard temperature and pressure at ground level. So we're going to need to have some way of accounting for that if we have an object of interest, a target that is not at ground level. So how do we go about doing that? Well, these altitude scaling factors correct three different things: pressure, distance, and time. So depending on what you're looking for, if you're looking for peak pressures, peak overpressure, you would need to use the S sub P. If you were looking at how to scale the distance from your target to the weapon detonation point, you would have to use SD. And if you were looking at something like shockwave time of arrival, you would have to use S sub T. So how do we put this all together? Well, let's take a look at a reasonable example. So in our reasonable example, we have a 25 kiloton weapon detonation occurring at 40,000 feet. Now, below it is a plane flying at 25,000 feet, and its ground range is 10,000 feet away. Now, we're just going to assume it's keeping a constant distance. It's flying a circle around the nuclear weapon. We'll go with that. It's flying a circle around the nuclear weapon. So at the exact point that the pressure wave reaches it, all these calculations will still apply. It's not very realistic, but it's close enough because remember that the overpressure is happening from the shock front. And the shock front is, it's not very big. It's a thin wall of compressed heated air. So, doing this for something that may be in motion, how accurate is it? It's a good enough estimate. We'll just go with that. All right, so what do we need to know other than the information that we've just been given? Well, the first thing we need to know is how far is the plane away from the detonation? What's this distance? So using the Pythagorean theorem and using these two sides of the triangle, okay, we can calculate what that distance is. And that's going to be the difference between the height of burst and the altitude of the plane, so 15,000 feet squared, plus the ground range, which is 10,000 feet. And if we do the maths, we get 18,000 feet. Okay, so that's the first thing that we can do based off of what we've been given. So let me go ahead and clean this up a little bit. All right, and I'm just gonna go ahead and write that number over here again so I'll remember what it was. Okay, so the next thing we need to take into consideration is that we have a high altitude burst, well, relatively high altitude burst at 40,000 feet, and our target is also at altitude at 25,000 feet. So from these two pieces of information, we can infer a couple of things. One, at 40,000 feet, the shock wave is not going to interact with the ground before it dissipates. So we will not have no shock reflection. So that tells us that we're going to be using one of our reference graphs instead of another one. The second thing we know is that our target is at altitude. So that means that we're probably going to have to account for the changes in the air at that altitude, because our reference graphs are all based off of sea level information. So what do we need to do? Well, we need to look at that table again. Okay, so it's important to note that this table and the information that you get off of this table applies to the target, not the detonation. Okay, so we're interested in the shock wave when it hits the target at the target's altitude. So that means we're not going to look up the information, the data for 40,000 feet. We're instead going to look up at the plane's altitude at 25,000 feet. Now, once we look this up, we might as well just grab all of the relevant data. So we're gonna write down, or you should write down the ambient pressure. Temperature's not quite as important. You're going to want the ambient pressure, you're going to want all three correction factors, and then you're going to want the local speed of sound. Once you have these things written down, we can move on to the next part. Okay, so now that we've gotten the values off of our table, let's go ahead and figure out what is the corrected distance or slant range that we're going to need if we're going to be able to read anything off of our reference table or reference figure. So we have an original equation that says that our distance is equal to the scale distance for 1 kiloton times the yield raised to the power of 1/3. Now, the only thing else that we're going to do here is we're going to add on that correction factor of SD. Now, we already have our distance, so let's go ahead and solve for our scale distance. All we're doing is moving stuff to the other side of the equation. Okay. So now if we plug the numbers in, which is 18,000, 25, and off of the table, this is 1.39. And we do the calculation, we find out that our scaled distance is going to be 4,435 feet. So I'm going to put that over here. And clean this up. There we go. Okay, so we know that at our height of burst of 40,000 feet, we're not going to have to deal with any of the reflected pressure wave. So that means we get to use the very first scaled plot that I showed you at the very beginning of the lecture, which is this one. So we have our scale distance of 4,435 feet. So we're going to do what we always do, which is put that, find that place on the x-axis, draw a line up to our reference curve, and then horizontal line for the reference curve all the way over to the y-axis, where we're going to find that our peak overpressure is about approximately 0.8 psi. Really kind of low, actually. But we're quite some distance. Our target is quite some distance away from our weapon detonation, and it's at a decent altitude. So we're reducing the effectiveness of the pressure wave, in addition to having the that distance, that separation distance. All right. So now we have our overpressure, right? So what do we do with that? We have a peak overpressure. Well, the next thing we might want to do is find out, well, what's our peak dynamic pressure? So a little equation just popped up here. So we're going to look at this equation right here. And we have two of the things that we need. We needed to know the peak overpressure, and we also need to know the ambient density, where our target is, which we read off of our chart. Well, it's not quite that simple, because one of the things that we're forgetting is that the overpressure that we read off of our reference figure did not account for altitude. Again, it's a reference for a sea level nuclear event. So what we have to do is, for an intermediate step before we can do our peak dynamic pressure, is we need to find out what the scaled peak overpressure is. And that's pretty straightforward. So we're going to use, get out of there. So basically all we're going to do is we're going to use the value that we've got from our chart, which is 0.8 psi, and then we're going to multiply it by the correction factor S sub p that we pulled off of our table, which ended up being 0.37. So this way we get a corrected peak overpressure of 0.03 psi. So now we can use this in our peak dynamic pressure equation, such that we get this 5/2, and then we have 0.03 squared divided by 7 times the local air density, which we read off of our table at 5.6, plus 0.03. And if we calculate it out, we end up with a peak dynamic pressure of 0.006 psi. And I'll go ahead and put what this was. So this is going to be our overpressure that's been peak overpressure that's corrected. And that's how you use all of these working pieces that we've gone over during this lecture all together to find out what's going to be the effect of a nuclear weapons blast, or what's going to be the amount of pressure from a nuclear weapons blast that is incident on a target at some distance away at some particular altitude. Again, the calculations are not super difficult. I would suspect that the most frustrating thing is making sure that you get all of the pieces lined up together properly and you don't miss a step. Like, it would have been very easy when calculating the peak dynamic pressure to forget that we needed to account for the peak overpressure being read at sea level, and that we needed to modify that before we could calculate the peak dynamic pressure. So the best way that I could say to set these problems up is simply ask yourself, what do I need for whatever is being asked? And, if you're given a slant range, then you don't really need height of burst, except to figure out if you're going to, which figure you're going to have to use. Are you going to use the simple one that I showed you in this example, or are you going to have to use the one that accounts for air-ground interactions? So it's important to lay out in advance of working a problem like this where exactly you need to go, and what do you need in order to get there. So that's going to be the end of this lesson. In the next lesson, we're going to talk about effects of blast pressure on different items, buildings, trees, electrical towers, that sort of thing, and how do we go from pressures, calculating peak overpressure and peak dynamic pressures, to the effects that these things are going to experience.